Imagine a major corporate client moves their headquarters across the country. In a standard spreadsheet, that customer's address is copied onto every single order they've ever placed. To update it, a human or a script has to overwrite thousands of individual cells, one by one. If a system crashes halfway through that batch update, the data fractures. Half the orders ship to the old address, half to the new one. Inventory gets routed to the wrong warehouses, and financial audits suddenly show two conflicting profiles for the exact same client. This is the baseline structure causing the problem, a bloated receipts table. You have the order ID and date sitting right next to the customer name, their address, and a crammed list of items purchased and prices. It is trying to do too many jobs at once. To stop data corruption at scale, we have to shatter this massive block of text. We use primary and foreign keys to fragment this chaos into a modular, linked blueprint. The first step is first normal form, or 1NF. A database cannot process repeating groups inside a single cell. We must mechanically split this list apart. Milk, eggs, bread drops vertically. Each item gets its own row, and order data duplicates to fill gaps. Visually, this looks worse. The table is now 3 times as long, and we've introduced repeating order numbers. But machines don't read like humans. A computer can now scan down a single column and count exactly how many cartons of milk were sold. By isolating these atomic values, we eliminate the need for error-prone string parsing. We can now accurately query individual items, allowing us to start building relationships. Identifying a row requires order ID and product ID, a composite key, but milk relies only on product ID. Second normal form demands data rely on the entire key. It slides out to form a standalone products table, leaving a foreign key. This brings us to a specific dilemma, the price. Does the cost belong in the master products table or the order receipt? If it lives in the products table, a price hike tomorrow retroactively alters past receipts, destroying financial records. The price paid must lock into the order record. We have successfully eliminated redundant master data while fiercely protecting the exact financial truth of every historical transaction. Third normal form deals with transitive dependencies. The rule is that a non-key column cannot depend on another non-key column. Take a look at what remains in the orders table. Which columns cause an anomaly if a client moves? The customer name and address depend on the customer ID, not order ID. They break away to form an isolated customers table. Remember the scenario from the beginning. In a flat spreadsheet, updating that corporate client's address required manually rewriting thousands of rows across a massive document. Now, that corporate address exists in exactly one single place. If the client moves, you update a single cell in the customers table, and every historical and future order automatically points to the correct, updated location. This diagram shows our completed architecture. A chaotic, vulnerable spreadsheet has been systematically disassembled into 3 distinct tables: purchases, customers, and products, all linked via primary and foreign keys. When a user asks for a specific receipt, the database software reaches across these lines, pulls the exact data it needs from each table, and presents it as a single unified view. It does this instantly, scaling effortlessly to millions of rows. To build a structure that scales, you follow 3 rules. First normal form, ensure values are atomic. Second normal form, data must depend on the whole key. And third normal form, data must depend on nothing but the key. This methodology was formalized by computer scientist Edgar F. Codd in the 1970s. His relational model transformed data storage from a physical filing problem into a strict mathematical architecture. By forcing your data to depend on the key, the whole key, and nothing but the key, you guarantee structural integrity no matter how large your system grows.